Hey guys, so today we are graphing logarithmic functions. So we're going to be graphing those logs. Before we get started with graphing though, we are going to go a little bit over our logs as exponentials and our properties of logs. So here we are writing each log. Sorry, we're writing as a log, and we've got these exponentials. So whenever we're converting, if we are using first, last, middle, it does have to be base first. So first, then last, then middle. So if you tried to go this way, it's all going to be wrong. So just make sure that you have base exponent equals a number. That's the order you want it to be in. So we would have log of base 10, 100 equals 2. Then on this one, again, we want to make sure that it's written with the base first, with the exponent, and then the number. So we got first, last, middle. Log base 3 of 81 is equal to 4. And here it's already written with the base and the exponent first, so then we're just going to go first. All of this is last, middle. So log base m of 9 is equal to x plus 3. Then when we are working the other way and we're writing them as logs, it's the same thing where we've got first, then last, then middle. So here we would have 2 to the power of 3 is equal to 8. First, all of this is last, middle. 5 to the power of 10 is equal to x plus 1. And whenever we don't have a base, remember that it is 10. So this is log base 10 of x equal to 6. So first, then last, then middle. This would be 10 to the power of 6 is equal to x. Now we're evaluating without a calculator. The easiest way to evaluate without using a calculator is going to be to convert. So this is first and last, and we want to find what it equals, so that will be our middle. So we have 8 to the power of something equals 64. And I know that 8 squared is 64, so that's an easy one. Otherwise, if we don't really know, we would want to write it as the same base. And then we see x equals 2, and x was what that entire thing equals. So log base 8 of 64 is equal to 2. So on B, we have 3 to the power of something is equal to 27. We want to write them as the same base. And 27 is 3 to the third. So that means x is equal to 3, which is that entire log. So log base 3 of 27 would be equal to x, which is 3. Here we have 5 to some power is 1/5. Writing them with the same base, we get 5 to the power of -1. So then log base 5 of 1/5 is equal to x, which is -1. So remember, our logs can equal negative numbers, but we can't take the log of a negative number. 2 to some power is equal to 16. We'll rewrite 16 with a base of 2, which is 2 to the 4th. So then log base 2 of 16, which is equal to x, is equal to 4. So that's how we would evaluate without a calculator. And we've got a couple more. 6 to some power is equal to 1. Anything to the 0 power is equal to 1. So log base 6 of 1 would equal 0. So that's one to be aware of. Anything to the 0 power equals 1. Now looking at f, this would be 9 to some power is equal to 0. Even if I take 9 to the 0 power, that's going to give me 1. So whenever we're looking at a log of some base of 0, it's something we can't do. Even if you typed this into the calculator, it would give you an error. Then on G, this is another one that we can't do because we're taking the log of a negative. So we cannot take the log of a negative number. So f and g are logs that we cannot work with. We can't take the log of a negative number. We can't take the log of 0. And then e is one that we need to know that anything to the 0 power is 1. Now with the properties of logs, we've got condensing, expanding, and then evaluating using the change of base. So on these condensing problems, we want to write them as one single log. So we have same base and minus. Minus tells me they're going to be dividing. So we have log of base 4, 32, divided by 2. We could leave it like that. But 32 divided by 2 is 16, so we could go one step further. Now on B, we're going to take those coefficients and make them into exponents. And then we're going to combine. So since we have plus, that's going to be multiplication. They have the same base, so we have x to the 6th times y to the 5th. And then we've got one single log. Now C is one that looks a little bit confusing just because there's so much going on, and I do think it makes more sense once we go over C on the expanding, but I'm going to work it out. So we know they all have a base of 10. I'm going to change the second minus to a plus with a minus that's being distributed. So once I distribute that negative, I know that the second one's going to be a minus as well. So we've got log x to the 5th y minus log z w to the 4th. And now that minus tells me to divide them. X to the 5th y over z w to the 4th. And we have our one single log. Now in the next section we are expanding these logs, so we want to get them written out as much as we can. On the first one, just right off the bat, I see multiplication and division. So I'm going to separate the division first. So division tells me to subtract. And then I'm going to separate that multiplication by adding. So log 4 plus log x minus log y. And so now I have an expanded log. On B, again, I have multiplication and division. But now I've got a power in there too. So then I'll take that power, make it a coefficient. And then that's as much as I can expand it. And then when we do C here, it's going to kind of make sense why we did the minus plus on this first step. So we've got log base 9. Oh, I missed my base on B. Log base 9 of AB squared minus log base 9 of C cubed D. I'm going to separate them. A plus log base 9 B squared minus log base 9 C cubed. Now here, this is technically added since they need to be combined with multiplication. But if I add it, then what happens? It goes on top. So in order to make sure that they're both subtracted, I'm going to distribute that negative like we did in C in the section before. So that way they are combined for C cubed and D to be multiplied, and then they are subtracted from the AB squared. Now since I have powers, I can continue further. I'm separating them by putting their powers as coefficients. Sorry, I didn't see that 3. I'm going to distribute that minus, and then that would be my final answer. Then on the next section, we are doing one problem where we evaluate using the change of base. So log base 81 of 27 would equal log with a base of 10 of 27 over log with a base of 10 of 81, which is 0.75. So if you had a calculator with without the ability to find what the logs are with different bases, and you had to use log base 10, then change of base formula is helpful. Now starting with the graphing, we are going to graph the parent function first, which is not on the worksheet. So the parent function is y equals the log of x. I am just going to kind of quickly go through and graph it. You would be able to graph this with a calculator if you needed to. We have a point at 1, 0, and then we have a point at 10, 1. So it goes this way, and continues up, and then we have an asymptote that is the y-axis. So it does kind of curve. So our domain, we see we're not going to get past the y-axis. So our domain is x is greater than 0. Our range, we're going to cover every single y, so it's all real numbers. Y-intercept, we're not going to be able, sorry, I said y-intercept, it says x. X-intercept is right at that point, 1, 0. We won't have a y-intercept, I'm sorry, because we are not going to be able to go through the y-axis because that is our asymptote, so x equals 0. So that's what our parent function looks like, and so dealing with the parent function first helps us to be able to move it around with these transformations. So on number 1, we're pretty familiar with our transformations at this point. So anything inside, we think opposite. So this is a transformation that moves to the right 1 unit. So since my parent function started at 1, 0, we're going to move to the right 1. So now we're at 2, 0. And we would move to 11, 1. This graph does not cover that. And my asymptote would also move 1 to the right. So it would be right there. So my domain would cover all of my x's that are greater than 1. And I'm not putting or equal to because we won't be able to hit that line. The range is still all real numbers. The x-intercept is 2, 0. And then the asymptote is x is equal to 1. Now, number 2, we have something going on the inside and on the outside. So we're going to move to the right 1. And we're going to move up 2. So our parent function starts at 1, 0. We're going to move to the right 1 and up 2. My asymptote moves to the right 1. Domain, x is greater than 1. Range, all real numbers. X-intercept. Now in order to find where that x-intercept is occurring, we know we have 0 for y. So we'll solve this equation. We'll move the 2 over. Whenever I don't see the base, I know the base is 10. I'm going to rewrite it with the log on the left. First, last, middle. 10 to the negative 2 power equals x minus 1. 10 to the negative 2 would be 1 over 10 squared. So 1/100th equals x minus 1. And 1/100th plus 1 is equal to x. So my x-intercept would be 1.010. Then the asymptote moved 1 to the right, so it is x is equal to 1. So the most difficult part on here will be to find those x-intercepts whenever we're given something like number 2. If you're given something like number 1, we're just moving it to the right, so we're not going to have an issue there. Now number 3, we're moving to the right 2, and up 1. So our asymptote moves to the right 2. Domain, x is greater than 2. Range is all real numbers. And then to find the x-intercept, it's going to be a fraction. We can see it's not going through a perfect point there. So we'll take log x minus 2 plus 1, set it equal to 0. Log, put the base in there, x minus 2 is equal to negative 1. Convert it, 10 to the negative 1 power equals x minus 2. 1 over 10 equals x minus 2. 1 over 10 plus 2 is equal to x. So 2.1 comma 0. And we can see that it's a little past 2 on the graph there, so we know that we found the correct x-intercept. Number 4, plus 2, so we're moving left, minus 2, so we're moving down. Our point is usually at 10, 1. So we're going to move 10, 1 to the left 2, which leaves me at 8, down 2, which leaves me right there. So this one actually fits on the graph. Our asymptote moved to the left 2. Domain will be everything greater than -2. Range, we're going to hit every single y very slowly but surely. Asymptote will be x equals -2. And then for our x-intercept, we're going to solve. So log x plus 2 minus 2 is equal to 0. Log base 10, x plus 2 is equal to 2. 10 squared is equal to x plus 2. 100 is equal to x plus 2. 98 is equal to x once we subtract that 2 from there. So our x-intercept is going to occur at 98, 0. So we see that we're going to very, 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 very slowly get higher and higher and higher. So we'll eventually get right here, all the way out here at 98. So it is slowly creeping up there to the x-axis, but we will get there. So then the remaining problems are for you to do, that's 8 graphs. Use your transformations. Use the knowledge that you already know about graphs in order to find what they should look like, what their domain is, what their range and asymptotes are. But then when you're finding the x-intercepts, make sure that you are setting it equal to 0 and solving by converting. So then that is it for today's video. Make sure that you turn this in on Canvas, and then I will see you guys in the next one.